And we looked at how we calculate internal energy, 3/2 nRT. And this is still going to be important as we consider our systems, because again, we have moles and they're at a certain temperature and they have a certain internal energy, and that's going to be really important here. If we look at the subtopic with thermodynamics again, this relationship with internal energy and work and heat is all going to be really important here. So internal energy is a property of a particular state of the system under consideration. If two equal quantities of an ideal gas originally in different states are brought into the same state, same pressure, volume, temperature, they all have the same internal energy regardless of the fact that they started at different states. And so that should be pretty straightforward there. Work and heat are not state functions. They're related to the change of state in a system, but not the state itself. And so yeah, so those are important to consider as well. Work and heat can affect the internal energy of a system, and but they are not state functions. So the first law of thermodynamics, we're dealing with internal energy system. And if we take our system and we put heat into our system, we know that the internal energy is going to increase. And so as that internal energy increases, that heat is causing that. So if we cool a system, the internal energy will drop. Now with work, if we take a gas, like that steam engine example, and if that gas is expanding, and it's doing work, the internal energy system is going to naturally drop. And so, but if we have a gas, like with a combustion engine, and we're compressing that gas, the internal energy will actually increase. So when we write out the first law of thermodynamics, we look at the change in internal energy of a closed system will be equal to the energy added minus the work done by the system on its surroundings. And so the change again here, change in internal energy is equal to the heat added minus the work done by the system. And that should make sense, because if you have a gas that's doing positive work, right, you're going to have, let's say it's doing positive 40 joules. When you place this in here, there's the negative already there, right? So the internal energy, and let's say there's no heat added or taken out of the system, an example, that's 0. If you did just 40 joules of work, the change in internal energy be 0 minus 40 joules of work, so you'd have negative 40 joules. And that would be the drop in internal energy. This gas would cool down, and that's what would happen, right? And so this is really the law of conservation of energy, written in a form of thermal energy transfer. So on the IB equation sheet, you'll see this Q equals delta U plus W, which is a rearranging of the equation. If you subtract W to the other side, you get the exact same thing. So the signs are really important in this law. If heat is added to a system, Q is positive. So if you're adding heat, it'll be a positive 10 joules, 15 joules, or whatever, that you put in there. If heat is lost or a system is cooled, then we have negative Q. And so, if let's say we cool it by 20 joules, we would have negative 20 joules for that. If a system does work is positive. But if there's work done on a system, right, so the system's compressed, work is negative. And so it's important to keep these in mind as we continue here. So with this one, the system absorbs 200 joules of heat from the environment and does 100 joules of work on the environment. So it expands. What is the change in internal energy? So as you draw these out, you can just draw a simple, one like this, where you have the piston inside the cylinder, and the gas is expanding, so the piston goes upwards, and it's receiving energy, though. It's receiving 200 joules of heat. So go ahead and use the ideal gas law. See if you can, not the ideal gas law, the first law of thermodynamics, and calculate the change in internal energy for this system. All right, so we should get, there's 200 joules coming in, 200 joules, and then it's doing 100 joules of work. So in that case, it's actually the temperature, the internal energy is actually going to increase, because even though the piston is expanding and doing work, it still receives more heat coming in, and so the internal energy will increase. Let's try this one with M4. How much work does the environment do on a system if its internal energy changes from 40,000 to 45,000 joules without the addition of heat? And so go ahead and see if you can draw the situation, and then then you can see if you get that. So go ahead and pause the clip and give this a try, and then when you're ready to check, you can hit play to continue. All right. So there's negative work, and in this case here, we're doing work on a system, so the volume is getting smaller. We have the change in internal energy, the internal energy final minus internal energy initial. There's no heat adding or leaving, and so there's negative 5,000 joules of work done on the system. And that should make sense, because the system now, it's a smaller volume, so we know it was negative work that happened here. And then therefore the internal energy increased as well, right? Because it went from 40,000 to 45,000 because the gas was compressed here. Let's try this one. M4A, gas does 450 joules of work on the environment. The internal energy only drops by 200 joules. How much heat was required for this to happen? So go ahead and pause the clip and try this one, and then when you're ready to check, you can hit play to continue. Okay. So the gas is doing work, 450 joules, and it says that the internal energy only drops by 200. So we have the internal energy dropping by 200. How much heat would that take? Well, it would take 250 joules of heat coming in. So 250 joules of heat coming in. It's doing 450 joules, so therefore it only drops by 200. So let's consider the isothermal process. This is where the temperature does not change. If we consider an isothermal process like this, where we have a gas that's expanding, like from A to B here, as the gas expands, the pressure is dropping, and that should be what happens, right? As the gas expands, the pressure will drop. Now, if it is isothermal, that means it's staying along the same temperature. And so, same thing with this one here, the pressure is dropping, the volume is increasing, but this is at a different temperature, a lower temperature. So, it's the exchange between pressure and volume. Again, these isotherms represent certain temperatures. So this is a cooler temperature, this is a warmer temperature, even the warmest temperature. So that's the initial state of the gas. Volume increases the final state of the gas. The pressure is dropping. And this is an isothermal process. So for an isothermal process to take place, we're going to have a heat reservoir to make this happen. And so, the system should remain in equilibrium, at least with this here. The heat's coming into it to make this happen, or it's being cooled if it's. Now, an isobaric process is where you have a constant pressure. And so in this case, let's take a look at an example. Let's say we have constant pressure here, but in this case, the volume is increasing, right? So from here to here, the volume is increasing, pressure is staying the same. And so we have that relationship there. So if we had that, right, we would be going from a cooler temperature to a hotter temperature. And that's really what would have to happen, right? If our gas here, right, is expanding, if this gas, is expanding, it's going to naturally want to drop in pressure. So if the volume is getting bigger, you'd have to heat it, and the temperature would have to be going up to keep it the same pressure. Likewise, if you're going the other way, if you're compressing a gas, you're going from here to here, and you have your gas and it's being compressed. If it's being compressed, then the temperature must drop to keep the same amount of pressure. So that should make sense there. So this would be called isobaric expansion. This would be isobaric contraction. Explosions, right? So this is called isovolumetric and isochoric. It's important to know both terms, isovolumetric, isochoric, same thing. but just different names express the same thing, but you need to know both. And so in this case, the volume is staying fixed. And so, if you have a fixed volume and the pressure is dropping, right, you're going to be going from a hotter temperature to a colder temperature. You're going to be cooling it. But if you have a gas and you have it at a constant volume here, right, volume is not changing, pressure is going up. Pressure is going to go up because the temperature is going up. And so, that should make sense. The adiabatic process is where all three change: pressure, volume, and temperature. So if this is an isotherm, if we have an adiabatic situation, the temperature, pressure, and volume all change. No heat enters or leaves. And so that's an important, part there with that. And all three will change. Now, adiabatic contraction is, again, where temperature, pressure, and volume all changes as well. And in this case here, you can see it going off of the, isotherm there. In an adiabatic process, no heat enters or leaves. And it's been shown that pressure times volume to the fifth third power is constant for monatomic gases. And so the pressure before should equal the pressure after in terms of that. So this is something that we can evaluate with an adiabatic process. And so, so we can see that. So this is M6A. We could try this. An ideal gas expands adiabatically from a state where pressure is 5 times 10 to the 5th pascals. The volume is 2.2 times 10 to the negative third meters cubed. The temperature is 485 Kelvin to a new volume of 3.8 times 10 to the negative third meters cubed. And we want to calculate the new pressure and the new temperature of the gas. And so, let's go ahead and try that. You can pause the clip and give this a try. When you're ready to check, you can hit play to continue. All right, so we have our gas before, gas afterwards. The gas is expanding. We have our values here in pressure and volume. And so we should get a second pressure of 2.01 times 10 to the 5th pascals. Once we have that, we can get the new temperature. Before, we got the situation before, situation after. And the temperature afterwards should come out to be 336.77 Kelvin. Okay, so for processes where the pressure varies, we can still get that area, and sometimes we'll have to approximate. For instance, in this case here, if we wanted to get the area inside here, we could set up maybe a triangle. Before, we really need integral calculus, right, to get the area underneath here. But, you can get pretty good approximations with what you need. So let's take a look at this situation. Let's say we have a gas. From A to B, what's happening here, right? The volume is going from volume 1 to volume 2. So this gas is expanding, right? So this gas is expanding. And from B to D, the pressure is dropping, but the volume stays fixed. And then from D to C, the volume is getting smaller and pressure staying the same. And then from C, let's see, A to B, B to D, D to C, and then C to A, right? C to A, the pressure is increasing, the volume is staying fixed. And so therefore, right, if we just looked at from A to B, right, we would consider this whole thing, this whole area, as work. But because there's some negative work done, right, so there's work done from here to here, going from D to C, we have to subtract that out, so the area inside is the actual work done in that cycle. And so, so let's take a look at this for this situation here. I want you to go ahead and graph this out just very basically. You don't have to set up the perfect scales there, but go ahead and sketch a graph with this and determine how much work is done in this cycle. So this is M7. So go ahead and pause the clip and give that a try. When you're ready to check, you can hit play to continue. Okay, so when we sketch that out, we should get a total amount of work of 50,000 joules. That's because, from A to B, we get this whole area, but from C to D, This is negative, it becomes negative work, or the volume is getting smaller. So we subtract that out, and it's just the area inside here, which will be 50,000 joules.